Let us see now the potential energy stored in an elastic string. This is sometimes called elastic potential energy, and it's abbreviated by EPE, and it's given by lambda. Now we square the distance moved by, the distance that we stretch that string, then we divide it by 2. Where is that coming from? It comes from the side. Work done in stretching a string can be got by multiplying the average force and the distance moved in the direction of that force. The distance covered by a stretched string increases from, before you stretch it, the distance is 0. But when you increase it, it increases from 0 to x. So this is what we call the x. So the force also increases from the force we are talking about, the tension. When we are unstressed, there is no tension on the string, so the tension is 0. But when we stretch it, we saw that our tension is given by this. So the force is also increased from 0 to lambda x over L. So to get the average of this, we get this plus this divided by 2. You know what we call the average. So this plus this divided by 2. This is 0 and divide this by 2. This 2 multiplies this L to get that. Then the distance moved, we shall get x minus 0, which is there. Then work done is given by the average force times the distance moved in relation to the elastic string there. So we get now the distance moved you've seen is x times this. Now it implies that this is going to be x squared, and so you see that's where that thing is coming from. So you see that the elastic potential energy is equal to the work done is there. Then this principle, we are going to apply it so much in the questions that are going to come in. The principle of conservation of energy in elastic string. There is a difference when I say principle of conservation of energy. We saw that. But this one is equal to the principle of we are adding of energy of an elastic string. If there is no work done against friction and the only external force which does work is gravity, then the total energy is given by potential energy due to gravity, then potential energy stored in the elastic string plus the kinetic energy is equal to the constant. What does it mean? It implies that the total energy, initial total energy, is equal to the final total energy. So here I'm abbreviating PE as potential energy and PE as kinetic energy there. So now this one, we are solving problems. This is the formula that we just set, and then we solve problems really easy. Let us start with the base of using this formula here. Let us see that example there. It says an elastic string of natural length 1.8. So in our solution, we read as we summarize the question. So the length is 1.8 meters and modulus 16 newtons. Is stretched until the extending force is this. So that means that it's stretched. So now that means that when we are stretching this string here, we are stretching it there until the extending force is, so until this force is 4 newtons. So that's what we have. Of course, we are going to be adding from here up to here. This is going to be 1.8 meters up to here. Then this is the stretch we've made, which is x up there. Now, it means that now, of course, this one is having t, and this one is having t in that direction. So now, until the extending force is there, now there it has reached the equilibrium. I think we start from there. Our t is going to be equal to 4 newtons, as you see from there. So when I have this, my t is equal to lambda x over L. So I have now my t as 4 equaling to lambda, which is 16, into x I'm looking for over 1.8. So that my x is going to be 4 times 1.8, the whole over 16. And so my x is going to be equaling to, so it's going to be 0.45 meters. So this is the extended distance of the extension. This is our part A. Then part B, they want us to get the work done. So that in our part B, our work done, I think remember the formula, it's there. lambda x squared over 2n. This is what we are adding there. So we have this, we have lambda, we have now the extension. It means that we have moved a certain distance. So this will be now lambda, which is 16, times 0.45, the whole squared, over 2 times our L, which is 1.8. So the work done now is going to be times so I'm getting 0.9. Another hour is mentioned in yours. So that's it. Pretty easy. I think you see. Of course, these are starting examples. They are always very easy, as you see. But as we move, we are going to apply more. So that's it. I wish you well, but please don't forget to subscribe to the channel. We are going to see now my examples from this and in the next lesson. So see you there.